Okay, today we're going to be talking about different phases. Okay, I've already told you I don't like the book. There are three phases, so I'm not sure why gases, which is what Rafe and Josette and Aaron and I do research on, how it got left out of this chapter. So I'm going to sneak gases in just a tiny bit, but for the most part we're going to talk about solids and liquids, which, as you can see up here, of course there is air in this picture, so I guess they didn't know they were talking about it all along. Anybody know why I have this here? Yes? Awesome. Thor is awesome. Okay. Any other reason? Does anybody know? Is this loud enough, or am I shouting, or what? Okay, yes. Lightning and plasma. You know, that's too deep for me. Okay, I'm a very shallow person. Yes. His name is Donald Blake. Thank you very much. Yes, Dr. Donald Blake. Yes, and so I had this grad student in '88 who kept calling me Thor and Thunder God. He was a very strange guy. He's still strange, and I never understood why until he gave me a 1969 comic that had Thor and then, you know, Thunder God, and then you open it up and there's Donald Blake, and then the next page is there's something that says, you know, Dr. Donald Blake will save the world, or something like this. And so Sherry Rowland was in my office, and when I showed him that, he just got this huge grin on his face, and he took the comic, and when I came back to my office later, on the door thing where it says who you are, and it says, before it just said Dr. Donald Blake, now it had Dr. Donald Blake with like a colored comic with the Donald Blake will save the world thing. I think it's still on my door. Okay, so if you come to my office, when you walk in, you'll see that, and plus this actually came out last year, I think, during this class. I think it was very, you know, so I won't be able to show this in 10 years, I guess. Okay, so we're talking about phases, and we live in a three-phase world. Okay, this guy right here has some water. Okay, we got water in the liquid form. There's also water up above in the gas form. Okay, up here. Okay, just so you know, all of these notes, everything from today except for the stories I tell, will go on the class website. I'm sorry that it's not on right now. I kind of had that flu thing, and I feel crappy. I felt weird on Tuesday. Not that you couldn't tell, but today I feel a little bit better, but I still feel kind of rotten. So I'm a little bit behind. But these notes, everything you see, will go on, and you can download it. And so don't spend a lot of time today writing down stuff, because you're going to have all this. Write down stuff that is like a little note to you. Okay? Anyway, we got three phases: gas, liquids, and solids. And all we have to do is change the temperature, and we can go from one to another. Gases. Okay? Gases assume the volume and the shape. So if I take some of this guy's water, all right, right now it's nicely contained. The liquid is right here. Any ice in here? No. No ice. So we have two phases. We have the liquid, and then we have some gas molecules that are up here. Now, if I take this and pour a little bit right here, oh, big deal. I'm the one who's going to trip. So now I got some liquid water on the ground. Now, unfortunately, it's kind of wet outside. The humidity is such that I'm not sure this is going to dry. Ooh. Yesterday when I did this, there was carpet, so you couldn't see it. But okay, anyway, the point is that this water may or may not evaporate completely in the next hour, but it'll certainly be gone by next time we have class. Okay? However, the water molecules that leave the liquid and go into the gas phase could actually still be here when we come back. You know, there's circulation and stuff, but there could actually be some. But what I do guarantee is that when, at the end of class, there are going to be water molecules that have jumped off of this liquid that go up and go all around and end up right back up at the back of the room. Okay? That's how gases work. Gases just like to be by themselves. They don't like to run into each other. They like to be, they like to ostracize themselves from everything. Okay? So, that being said, that means that they have a huge volume that they take up. Okay? Whereas the liquid that was in that thing was this big, and if it were solid, if we were to freeze this thing, okay, if we were to freeze it, that volume wouldn't change much. Okay? Liquid and solid, very little. It's very important later on, and we'll talk about this, but there's very little difference between that. And yet, gas-wise, huge volume. Is anybody, I'm going to give you a rule of thumb. I also want to say this, that in this class, folks, I am interested in you learning generalizations, okay? I'm less interested in the exception to the rule, okay? If something is right 95% of the time, that you can use this rule, or this is always bigger than this, okay? If there's an exception, I will let you know, but I'm less worried about you being able to come up and tell me about the exception. If you're a chemistry major, and you go on and you take physical chemistry and some other things, you can then learn about the exceptions and why they are exceptions. But for right now, I just want you to be able to conceptualize what it is that we're doing, okay? And that generally speaking, this is the trend, okay? So I'm going to tell you something that either may help you during this class, I don't know, but it'll help you sometime in some chemistry class. Rule of thumb. Gases take up about 1,000 times more volume than a liquid. Okay? About 1,000. It's not exactly 1,000. It's about 1,000. For some gases, it's 1,500. For others, it's 500. Okay? But it is on the order of 1,000. So if I take that half a liter of water, okay, that was in that bottle, let's say it was full, if we let it, that would actually fill not a half a liter, but 500 liters. 500 liters of water we would have in a vapor phase. Okay? So those molecules are far apart as opposed to right next to each other. In fact, how many of you ever heard of the ideal gas law? Okay, that just means that basically one molecule doesn't even see the other. That's a non-ideal thing. Things kind of go non-ideal when you start pressurizing them. But in this room right now, just about every gas is in an ideal form. Okay, they're far enough apart. Yeah, they hit each other occasionally, but it's nothing like when you're in a closed thing like a liquid. Okay, so a factor of 1,000. All right. Who can tell me, so as an example, who can tell me what is the molecular weight, what is 1 mole of water? 18, he says. 18 grams per mole. Perfect. Okay? 18 grams per mole. Now, so we go from 18 grams. Now do we remember, and you may not remember this, but 1 mole of a gas is 22.4 liters. Okay? 1 mole of gas at STP is 22.4 liters. So 22 liters versus 18 cc's. So if you do the Don Blake thing, 18 times 1,000, that's 18 liters. Pretty darn close to 22. Okay? So the point is that gases are huge. Okay? They can therefore be compressed. Okay? If they've expanded, then you can compress them. That's why you can have a compressed air tank or a scuba tank that's at 2,000 psi. They compress easily. Liquids, on the other hand, do not. Liquids, you can't make them compress very well at all, nor solids. Okay? The density, because gases can float all around, their density is very low, and therefore they're very compressible. Density of these guys is high, and they really are not compressible at all. These gases, as I said, some of the water is at least from me to Rafe right now. That's how far it's gone. for sure, gas molecules. This water hasn't moved, okay? So as far as motion goes, in a gas, free motion. Here, 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 all around the room. Water, I can slosh it around here, okay, and it can roll around and roll past each other. Okay. If it were a chunk of ice, though, I would sit it right here and it would just sit right there. So chunk of ice they're fixed and they vibrate in position. Kind of like you folks. You guys are like in a lattice structure right now. Okay. Every one of you is in a seat. A little fidgety maybe. Okay. But you're not moving. Okay. And you don't move until you get enough energy, enough kinetic energy to move out of that seat, which is the energy you get when we get close to the period being over. Okay? When I say class dismissed, boom. Everybody gets up and you become a liquid. Okay? You go from being solid to liquid. Okay? So once again, you can kind of move around a little bit, but that is it. And that's what we're going to be talking about, structure of solids and liquids mainly in this one. And turns out that you are a solid, liquid, or gas based on the interaction of molecules with molecules. Okay? So this guy's name is van der Waal. Jonas van der Waal. And he came up with these forces. I'll just put them all up here real quick. Said that there are 3 types of forces. There's a dipole-dipole. We're going to go over all these, trust me. And that's where you have a polar molecule and a polar molecule. Sort of aligning the negative end with the positive end. And then you've got polar molecule ion. So this is a dipole-dipole. Then there's ion-dipole. And then you have something where it's like a dipole-induced dipole, which is where you have something with a little bit of charge, and then it just sort of passes by somebody or something, and it just causes like a little instantaneous charge differential. And so that happens between a polar molecule and an unpolar molecule and an ion and an unpolar molecule. And the dispersion is basically everything's got dispersion. Everything. So the reason why things are solids, liquids, and gases are dependent on how strong these forces are. The stronger the intermolecular forces, the more they want to be together. Okay? So this is just an overview. We're going to now go through each one ad nauseum. So this picture right here is like the class, right here. Here we are. Okay? We are in each little seat. Okay? And this is what a solid would look like. And then this is like, in this direction would be like giving it energy. Okay, so over here I give this a little bit of energy, but it's so cold, nothing happens. Energy cold, nothing happens, nothing happens. All of a sudden, right about here, I look up here and there's one little molecule right there that looks like he's getting ready to take off. Then we go to this one. Here's one, and there's one, and a bunch of them. So right about here is where we have a phase change. We're going in this direction from solids to liquid. Okay? That's what happens. Give it enough energy, you know, and we know that. Take some ice, put it in your freezer. Don't do this, but if you put it in your freezer and you get in the freezer, it's not going to melt. Okay? You watch it, it's not going to melt. As long as you're in the freezer, a walk-in freezer. Okay? Put that piece of ice right here, and you can sit and eventually watch it melt. And you're going to watch it just do this. Okay? The outside is going to melt first, right? Why? Because it's the outside that's getting the energy from molecules in the air. And it just sort of slowly melts outside toward the inside. And that's just because of the energy that it's getting. Okay, and once again, kinetic energy is equal to 3/2 RT. So as you increase the T, at some point you get enough kinetic energy to jump out of the seat. Okay, this is very important. This is an almost for sure multiple choice question on the exam. True or false? Okay. And that is going to be, you've got intermolecular forces. Inter means between molecules. Intra means within the molecule. So intermolecular forces, once again, are the attraction of, let's say, this young lady here and this young lady here. Okay, those two, or this young lady and this guy, okay, somewhere that's sort of close, all right? That's that interaction. Intramolecular would be, you know, your arm and your leg, okay, within the molecule itself. And so you have bonding that we're going to be talking about here, which is the force that holds molecules together, and then you're going to have bonding like covalent bonds, which you've learned about, which are the bond that holds the hydrogen to the oxygen. Okay. Very different. The question would be something like, intermolecular forces are the forces, you know, true between molecules or within a molecule. You're going to say intermolecular is between molecules. So, if I take this water that's on the ground right now and I get a hot skillet and I pour it in there, I have to put in 41 kilojoules to vaporize 18 grams of water. If that water's already at 100 degrees, okay, it takes another 41 kilojoules to heat it up and get it to vaporize out of there. 41 to get it to go from a liquid to a gas. 41 kilojoules, all right? Now, that's the intermolecular forces. It's those forces that are causing it. Cost me 41 kilojoules to get that water to separate from itself. However, to break all the OH bonds in 1 mole of water would cost 930. So it's like 20 times more. So intramolecular bonds are much stronger than intermolecular bonds. Okay. Now, I'm not saying that there's not some inter that are close to intra, but generally speaking, intermolecular forces are much less than intramolecular forces. Generally. And all of these things, which we will get to later, boiling point, melting point, vaporization, fusion, and sublimation, are all functions of intermolecular forces. Okay? So once again, the intermolecular forces, the stronger they are, the less likely something is going to want to go from one phase to another. Okay. So, I looked in the book. How are you supposed to know when something's got a plus end and a minus end if you have not been taught electronegativity? And I looked in the book, and like the first time they talk about electronegativity is on page 613. I believe that's about a dozen chapters after chapter 5. So I'm going to have to, I've got some electronegativity, just general electronegativity stuff, to show you how you determine whether something is, why you got a negative end and why you got a positive end. Now, most of you should have heard the word electronegativity. Whether you understand electronegativity or not is another thing, but you should have at least heard of it. But what happens is that if you have a situation like this is a dipole-dipole. This is where a molecule has a sort of a positive end and a negative end. These are little tiny charges, folks. This is not like a whole plus charge or a whole minus charge. It's just a little bit. It's like you're loaning a little bit of money to a friend. You don't give them everything. You give them a little bit of money. Okay? And that's what's happening here. Within this molecule, this side has taken a little bit of the electron density. Okay? But it's maybe only, 1 or 2%. Okay? Very, very small. But if you do have a situation like this, then you end up with an orientation that looks like this. What is this? Negative end, positive. Negative end, positive. Negative here, positive there. See how they're lined up? This is a much more energetically favorable than if you had a plus here, minus here, and a plus here, and a minus here. That's like taking two magnets. Have you ever done that? How many of you have ever, I want to see raise of hands, ever taken a magnet that was like a horseshoe magnet or something and went like this? You cannot, unless you're Superman or Thor, you cannot put magnets together. Now, if you put a north and south, you have to do nothing to get them to go together. But you try and get them to go together like this, and they start to repel each other right here, and it really is hard to get them to do this. Okay? So this is much more favorable. This is the north-south. Magnets going together like that. Much happier like that than trying to force them like this. That's what this is like. And in a situation like this, this is where you have a dipole-dipole interaction, and you've got the positive ends trying to get as close to the negative ends as possible, and vice versa. So, folks, this is a general thing. Okay? You do not need to write this down. I want you to just try and understand that on a periodic table, generally speaking, electronegativity gets stronger as you go from the left side to the right side and from the bottom to the top. So fluorine is the most electronegative. The most electronegative, and francium is the least. Okay? Generally speaking, this is how it goes. And what it means to be electronegative means that you really you don't share well. Do you ever know a kid like that? You ever know a person you grew up who just didn't share well? They wanted to play with your toys, but they wouldn't let you play with theirs? Okay, that's what fluorine is. Okay? These are the spoiled kids up here. And these are the loving, wonderful, giving people. Yes?
So the noble gases are...
Noble gases have no desire to do anything.
So
these are, I was going to say something. I can't say it because I'm being filmed. But the point is that these are like not even in the ball game. Okay, they are so happy with the electrons that they've got and the matchup and everything, and their shells are filled, that no, these have zero electronegativity. In fact, these, we'll talk a little bit about some of these, but they're very happy. So fluorine is the most. Okay, now if I were to ask you, I'm going to ask you, this lady. So, yeah, you're hoping it was him. Okay, so if we look at this, would you say oxygen is more or less electronegative than aluminum? More. She's right. So looking at this, anywhere sort of down here, you can make a general statement like that. But if I'd have asked her, is oxygen and chlorine? Ooh, that's a tough one, because this one's higher, but this one's further left or further right. Okay? So I'm not going to ask you on an exam to know whether chlorine and oxygen, which one is more electronegative. But what I will ask is whether something up here is more electronegative than something here, or something here is more electronegative than something over here. Okay, yes?
You said you won't ask for which one is more.
I'm not going to ask, there won't be an exam question that says which one is more electronegative. No. I want you to understand that these up in here, they want to yank electrons. And things like hydrogen, carbon are less willing, they're more willing to give up an electron. Okay, because in the fluorine is just the worst. HF is a very, very unsharing. I mean, or the F is pulling electrons away from the H. Okay, because it's here and the H is higher, but H is kind of weird. H is sort of in the middle. Okay, and when I was a high schooler, fluorine was given a value of 4.0, and hydrogen I think was 2.1. So clearly the fluorine yanks the electrons toward it. So I would not, the question I would ask is that if you had a bond, and we're going to do this in a minute, a bond of CBr or CF, is it going to be polar? We'll go over that. Ask me this question again in a minute, okay? But generally speaking, this is electronegativity. Unless you know that something doesn't share well and wants to have the electrons, I don't know how you can tell that something's polar or not. So, question. What is the electronegativity difference between carbon and oxygen? Okay? Which one, looking at, generally speaking, okay, you don't need this arrow anymore. Just remember it goes like that. So you're going to have a periodic table on the exam. You're going to say, okay, things up in this corner. Oxygen is almost in the corner. Carbon is over here. Therefore, oxygen is more electronegative than carbon. So if you have a CO bond, O is pulling more of the electrons toward it. So that's going to be the negative end. And the carbon, having lost electrons, now becomes a little bit positive. Okay? So, look at carbon dioxide. So I just said that the oxygen is going to pull harder. Okay? So if you draw the charge distribution here, here's the central carbon and here's the oxygen. And the way we draw it is the plus, you draw the arrow and then you put the plus, the cross thing here like it's a plus, close to the side that's the positive side. And the arrow goes toward the negative. So here we have an internal dipole moment that has the electrons going this way. Okay? However, equally charged going this way. So if I stood up here and I asked two people to come up to the front of the room, two people of absolutely equal strength, and I asked them each to pull on my arms just like this, would I move? In theory, I wouldn't move, right? I wouldn't move. Now, if I were like this and they pulled, I'd move like this. Okay? But when you're pulling direct like this, so if you can have a bunch of little internal dipole moments, but the molecule itself, look at this. You can't draw an arrow that would show which way was positive or negative here. So this has no dipole moment. No dipole moment. Therefore, it's not a polar molecule. Okay? This has no dipole moment. Okay? And if you remember in VSEPR, we have all the electrons are centralized all along here. If, however, we go to water, VSEPR tells us, okay, even though this has just an H and an H, and you'd think that it would be just like CO2, we got bunny ears, okay? And they take up a lot of space. And so instead of it being linear like CO was, all of a sudden you've got something that's pushing these hydrogen covalent bonds like this. Something is behind you pushing. So now, if you've got something like this, clearly this is negative here, this is positive here, and I think the next slide will show this then is what the dipole moment looks like. You've got little dipole here, and the overall one, you draw it right through there. Negative end, positive end, just like that. So this has a dipole moment. And therefore, it can have dipole-dipole interactions. And dipole-dipole interactions are pretty strong. Okay? So if something has a dipole moment, then it's a pretty darn good chance it's going to want to stay with its friends. Okay, it's going to stay in the solution or whatever. Okay, so ion-dipole, this is just, okay. So this is a whole ion. This is a whole charge, folks. Okay, a whole charge is a whole lot more than we were talking about on this thing. Okay, this negative here on water is like a 20th of a charge. Okay, this is a whole charge. This is, if you put like sodium iodide in water, it's a salt. Put it in water and you'd have the negative end or the oxygen end of water going toward this, and the positive end, which is the hydrogen end, toward this. Okay, this is a very strong bond because you have a whole charge. You know, I haven't talked about Coulombic, the equation. Okay, but charge is very important. Charge and distance is huge in that equation. So here you got a whole charge, here you got a little tiny charge. And so an ion-dipole interaction is very strong. And that's why if I take some table salt, and put it on this table right here, and we walk away, nobody touches it, will it be here when we come back on Tuesday? Will it be here in a year from Tuesday? Yes. Will it be here in 100 years? Yes. I mean, salt is salt. I mean, it's very happy being in that crystalline form. And yet what happens when you put it in water? It just disappears. Right? And that's because of this. Okay? That you have water that actually can sort of grab from the outside, just like the ice melted. You put salt in water, it starts to be pulled apart from the outside. Okay? It gets pulled apart, because you can have a bunch of water molecules around the sodium and a bunch of water molecules around this. And actually the energy is actually more favorable in a situation like that than the salt was just very happy sitting as a solid. Okay? So ion-dipole, very strong, generally speaking the strongest intermolecular force. So I don't agree with this, so if we have a sodium here, let's say we have a sodium there, you can put all of these water molecules. So this is a plus right here. So the negative oxygen, the negative end of the water, the negative end of the water, negative end of the water, water can go around this thing. You fit sort of 6 different molecules, let's say, of water around that one sodium plus. Very strong. Okay. Same thing around, if we wanted to draw it again, we could put the negative here, and then it would be the hydrogens that would be going toward it. Okay. So guess what? Have you ever put enough salt in water that it didn't dissolve anymore? You know why? You know why there is a certain limit to how much salt you can put in the water? Okay, right here, if you've got 6 waters around that sodium, then that is more favorable than the piece of salt sitting as a solid. But if you go to 5, it's not. So if you put enough salt in the water so that you end up limiting, so you only have 5 water molecules instead of 6, the salt says, hey, that's not enough of an option. I'm going to stay as a solid. Keep pouring salt in, just keeps piling up. You ever been to the Dead Sea, anybody? Dead Sea? Okay. Go to the Dead Sea, you walk on about this much salt. Salton Sea, the same thing, okay? Very salty. And that's just because there's not enough water. Make the salt go away if you just put a bunch of water in there. Okay? And that's what this is. Now this one has a 2 charge, +2. So this has strong interaction, yet it's stronger. It should not say weak and strong. Relative to this is weak. But relative to just about everything else, this is strong. Okay? Ion-dipole is strong. But as you change the charge, then you got a +2 charge, then this interaction is much stronger. Okay? But ion-dipole, strong. And this is what it looks like in a different form. Okay? You got the plus end going toward the anions and the negative end going toward the cations. Dispersion. Oops. Dispersion, everybody has dispersion. Every molecule. Okay? That's very likely to be on the exam. Every molecule has this type of intermolecular force. Ion-dipole, dipole-dipole, dipole-induced dipole, dispersion. Okay? It's going to be dispersion, okay? It's this very little tiny induction. Because on the molecule, you know, we're not talking about xenon, okay? We're talking about something like, well, not DNA, but something that's got lots of carbon, hydrogen bonds and other things on it, okay? And there's little tiny charge differences, and you can actually induce just like that, okay? So everything has dispersion. So you can induce a dipole, okay, with something that really doesn't have much. So you can, this is a neutral molecule, there's no dipole moment. But you put a cation next to it and you can sort of tease a little bit of the electricity, or the electrons to go in one direction, okay? One direction or the other. Same thing, you can also get a dipole-induced dipole. Okay? Now, it's not very strong usually, except if it gets big. So this is what it looks like, okay? Not polar. You got these guys just sort of floating around and they're just sort of aligning themselves. There's these temporary sort of oscillations in charge. And so little charges all along its backbone, and just instantaneously you end up with a little bit of a positive in one area, a little bit of a negative. And that is fleeting. It's always changing, but it's going throughout the molecule, and so dispersion is important. So let me ask you this. Do you think dispersion is bigger in a little round molecule or a long dangly one? Okay, if I were to ball this thing up, and I asked somebody to come up and stand right here, and I was going to drop it and they were going to catch it. Okay, it's all balled up. I said catch it. I drop it. Would it be easier for them to catch it and drop it like this, or if I did it like this? Or like this? I could even catch that. Watch. See, I didn't even know I was going to drop it and I caught it. But I probably couldn't do it if I did this, even though I know I'm going to drop it. Okay? So the point is that you got something that's kind of long and dangly or big and fat, you can grab it easier. Okay? And that's what dispersion is. Okay? It's this little temporary stuff. Very temporary. A little bit of a plus charge here, a little bit of negative there, a little bit of negative here, a little bit of positive here. It's kind of like you can't make your mind up. Okay? Somebody calls you up, says you want to go to a movie, you want to go do something. You know, part of you is saying yes, part of you is saying no. Have you ever been in a situation like that? Where you're not quite sure you want to go. There's good reasons to go and there's good reasons not to go. Okay? And that's this. Fickle. Fickle. Dispersion is fickle. Okay? So, but dispersion rules the day. Okay? Look at this. So we have a carbon with a hydrogen, 4 hydrogens, 4 fluorines, 4 chlorines, bromines, and iodines. Okay? Now, this is not, methane is not a polar molecule. That is because even though there's a little bit of charge difference, I think this is on my old scale was a 2.5 on the electronegativity scale, and this is a 2.1. So there's a little bit of a charge difference. So there's a little bit of electron density toward the carbon instead of the hydrogen. But I got 4 of them all pulling exactly on me so that I'm not moving, just like it was with the carbons, or the oxygens with carbon dioxide. So there is no net dipole moment. So these do not have a dipole moment. Okay? Even though, look at this. Fluorine hugely wants electrons, right? Hugely wants electrons. But if they're all being pulled in the same direction, it is not a polar molecule. Okay? You cannot draw a dipole moment for CF4 because you got some negative going this way, and some negative going this way, and some negative going that way, and some negative going this way. And you're like got 4 ropes on you, and they're all pulling at the same strength, and you're not moving a bit. That's what's happening to all of these. Okay? So the only difference, folks, is that what is bonded to the carbon here is getting bigger. Okay? Bigger, more electrons, more mass. And look at it, methane melts at 182 below. That's cold. That's brutally cold. Okay? So you replace a hydrogen with a fluorine, and you are 32 degrees warmer when you melt. CCl4, you know, you're cold, but, you know, 23 below zero. I was at the South Pole, it's colder than that. Okay? So what that means is CCl4 would be a solid at the South Pole. CBr4 doesn't melt till 90 degrees, almost boiling. And CI4, 171. So CI4 would just sit right here on the table just like a chunk of salt. Okay? Because it's not going to boil till you get to 171 degrees C. All of this, folks, is because of what is attached to the carbon and the fact that this is big and lots of electrons, lots of mass, and is polarizable and has these little instantaneous things where it will loan and borrow and take electrons. Okay? So in this case, size matters. Okay? In this case, not just size but shape. We're going to get into some shapes in a minute. But generally speaking, the more electrons, the bigger mass, the more dispersion. So I should be able to just give you a question that says, okay, CF4, CCl4, CBr4, and CI4, which one has more dispersion? And you're going to say, this one, CI4. Because if you have a periodic table, like you will on the exam and you got on the walls here, you'll say, oh, iodine is the heaviest. It's the furthest one down. Okay, it is by far the heaviest. Okay. How are we doing on time here? So how many of you think you understand this? And not many. Okay. So let me give you some analogies. Okay. Intermolecular forces, in terms of changing phases, that's what it's all about. Okay? If you have strong intermolecular forces, then you're happy in the phase you're in. If you're not, if you have weak intermolecular forces, then a little bit of energy and you're gone. So think about it as you're at a party. Okay? You're at a party, and it's a party with a half a dozen of your best friends. Okay? How many of you have ever been to a party like that? Okay. Get some friends. So, half a dozen of your best friends. Now, how many of you have been to a party where you're at a party with a bunch of people you really don't like? Yeah, more. Jeez. So let me ask you this. Those who, okay, now, how many of you who raised your hands both times, raise your hand? Okay. So those who raised your hands both times, so you've either been at a party with lots of good friends and people you didn't like. Now let's just assume that at the party where you had people you didn't like, there weren't a lot of your friends. Okay? You're shaking your head like you understand that, right? You, yes. Okay, so I'm going to ask you a question. Which party were you more likely to leave early? The one where you didn't like anybody and they didn't like you? Maybe that's a problem. Or the one where you have a lot of friends? The one where you didn't like anybody, right? Or certainly not the one where you got friends go, oh, don't leave, don't leave. That happens to me all the time. I don't go to parties. So that's what intermolecular forces are. That is all it is. It is what attraction is holding you where you're at. Okay? And so if you are strongly being held by dispersion, by dipole-dipole interaction, by ion-dipole, whatever it is, and they add up. Okay? Doesn't have to be your best friends. It could be somebody new you just met. There's lots of different things that would keep you at a party, and then there's other things that might make you leave. Okay? Maybe it's not just that there's people who you don't like, but maybe you just heard that somebody at the party has a disease. Or the flu. Okay? Or an eye infection. Something that you don't want to get. Okay? That has nothing to do with how much, maybe it's even a friend of yours. Okay? Maybe it's your best friend. Doesn't matter. All of a sudden, that intermolecular force just got a lot weaker. You know? Or it's a friend of yours who wants to borrow money. Okay? So, it all adds up. So you have to consider everything. Not just one intermolecular force, but all of them. Okay? Because it is. She's yawning right now. Okay? It's okay. It's perfect. Because she might be at a party, same people, but she's tired. How many of you ever left a party because you're really tired? Yes. Okay? Maybe you didn't want to leave, maybe you were having fun, but maybe common sense took over and said, oh, God, you know, Professor Blake's giving an exam tomorrow, I shouldn't be partying, you know, I really should be sleeping, you know, or studying. So there's, you got to add them all up. So folks, that's what it is. It's, think of the party, okay? What is holding you in the party? What is helping you push toward the door, all right? So, some of you had Professor Sassingham last quarter. He loves Lewis dot structures. Okay, you love him. Okay, good. So, Lewis dot structures are nice because they do, particularly with VSEPR, they tell us whether a molecule is, what its shape looks like. Okay, so you do need to know something like that. In the case of HBr, okay, It's only two things. It's got to be linear, right? It's linear. Two points. You can't make 2 points not be straight. You add 2 points then, or 3 points, then you can start doing this. So this one has to be linear, okay? So I'm going to ask this person right here, you right there with the blue Volcom shirt. HBr, do you think it could be polar or nonpolar? There's Br right there. Okay, so it's on this side, so it's kind of electronegative, and there's the H. Br is a little bit more electronegative than an H. So what's the answer? Polar. Thank you. Yes, polar. With these electrons coming a little bit more toward the bromine. Methane, I already told you. Methane, here's hydrogen, here's carbon. You know, this is more to the right, this is higher. They're pretty similar, but actually hydrogen's a little bit less, I think. So the carbon actually pulls a little bit of the electronegativity toward it, but not much. But it's this. It's tetrahedral. Everything pulling exactly against each other, so nothing moves. Now all I'd have to do is if I added a fluorine to that, one fluorine, all of a sudden it becomes polar. Get rid of one hydrogen and replace it with the fluorine, because that fluorine is going to now pull, and instead of me being like this, all of a sudden this one is pulling hard like this. I'm a crappy dancer, so don't give me dancing. Okay. So I'm not going to give you, there will be a periodic table on your exam, folks. Just want you to remember, this is what electronegativity generally looks like. I'll ask you nothing that asks you to differentiate between, you know, this one and this one, or this one and this one, okay? That's too tough, okay? So, CH4, if it's completely linear, and it's got the same type of electronegativity pulling in each direction, which is hydrogen, 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 then there is no dipole moment. SO2. I think I do it for you here. There. Uh-oh, that's where VSEPR comes in, because we might have thought that this was going to be linear like CO2. But because we only have one bond here, whereas with carbon we had two, a double bond, these bunny ears sort of push this a little bit this way. So the dipole moment, these guys, these sulfurs, or these oxygens, oops, I don't have a periodic table, are more electronegative than the sulfur below it. So this becomes positive, this is negative, so it's got a plus here, and you draw the arrow down like this with a plus charge up here. So it is polar, okay? So it's got a dipole-dipole interaction. So in this case, we have dipole-dipole and dispersion. In this case, we only have dispersion. In this case, we have dipole-dipole and dispersion. So don't forget, everything has dispersion. Everything. This is just an example. This is, I believe, pentane, C5 somewhere. Pentane. This one's pentane. This one is a C15 compound. It's kind of like syrup, okay, a lot more viscous. And this is like waxy stuff. All we did was go from a C15 to a C18. Added 3 carbons, and it went from being goo, so it went liquid, goo, and wax. With just adding 3, all because of dispersion. It's just carbons and hydrogens. That's all there is. So there's no dipole moment. But look at what dispersion does. It can actually make hydrocarbons into solids. So dispersion, folks, you can't say that, you know, ion-dipole is stronger than all dispersion. Generally speaking, dispersion is weak, but the bigger the molecule gets, like a DNA, you know, DNA just sits, okay? Doesn't want to be a liquid. So this is the difference that chain length and some floppiness can give you. And this is what it looks like. Is basically, if you got something that's kind of long and stringy, you can have more of an interaction here. These round ones, you have much less surface area. The volume of this is the same as that. But you see there's just a little interaction here and here. So if you got something that's kind of long and stringy, it tends to have more dispersion than something that's just round. Okay, now we're going to talk about hydrogen bonds. This is a special kind of dipole-dipole. Now this is what you got to remember. It only happens with 3 when you got 3 things involved. A fluorine, an oxygen, and a nitrogen. That's it. 3 things, okay? You must have a hydrogen attached to a fluorine, a nitrogen, and an oxygen. Okay? It's got to be attached to one of those. It can't be a hydrogen stuck on methane. Okay? So here we have a hydrogen attached to an oxygen. Here we have a hydrogen attached to a nitrogen. And here we have a hydrogen attached to a fluorine. It's only when you have that situation. So the hydrogen, folks, that is involved in hydrogen bonding must be attached to one of those 3 atoms. Okay? Or it doesn't happen. And what happens is that that hydrogen that is attached to the oxygen, the nitrogen, or the fluorine, because of the electronegativity of this pulling electrons toward it, so that this is a positive end, negative end, positive end, negative end, positive end, negative end, actually sees the electron lone pairs. Look at those lone pairs sitting there, sitting there, sitting there. Sees it on on another oxygen, nitrogen, and fluorine, and goes for it. It's a very strong bond, intermolecular force bond, but it's still a strong bond, okay? So it only happens if you have oxygen, nitrogen, or fluorine. And they can line up like this, and they do line up like this. So you must have the hydrogen that's involved, folks, has to be attached to oxygen, nitrogen, or fluorine. Okay? So something like methane, CH4. Can it hydrogen bond? No. It's got 4 hydrogens. But are there any hydrogens that are bonded to an oxygen, a nitrogen, or fluorine? No. Therefore, no hydrogen bonding. Okay, look at that. Methane. First of all, it's linear. Second of all, there's 4 hydrogen bonds, 4 covalent bonds, okay? But we're not talking about, yes?
Why can't you have something like a hydrogen bond with something like fluorine? Because that's pretty close to the electronegativity of oxygen, right?
Okay, so his question is why fluorine and why not chlorine? Right? I will show you, okay? I think in another minute or 2. So, don't be tricked. Don't be tricked that something with a lot of hydrogens on it cannot form an intermolecular hydrogen bond, okay? They are intramolecularly bonded to the carbon, okay? Those are all very strong bonds. 400 joules to break a mole of those bonds, okay? But they do not hydrogen bond in an intermolecular force way. And this is what water, okay, so here's water and here's water and here's the negative end looking red and red here, and you can see that this is an oxygen here, so you got a positive end here, you got a positive end here where it's blue, and so the blues tend to line up where the reds are because of the interaction between, once again, the electrons that are on this bond right here. So you got this oxygen, hydrogen, so that fits the description, and then this oxygen has some lone pairs out here, and so this is where the hydrogen bond is occurring. And oxygen, or water, folks, can hydrogen bond twice. Okay, so why does water have a higher boiling point than HF? Okay, why would this has even more polarity to it. Okay, dipole-wise, this is stronger. Okay, but which one is going to have a higher boiling point? Which means which one wants to leave the party last? Which means which one has more attraction? Okay. Well, this has hydrogen bonding and this has hydrogen bonding. This is a little bit bigger, so dispersion-wise, this would maybe win. But which one? Water can actually form 2 hydrogen bonds. That's what makes it so strong. Water can actually form, you can have 1 hydrogen looking at the lone pair of this one here and another hydrogen going for the lone pair over here. You can't do that. Fluorine only has 1 hydrogen. So it cannot do that. Okay? So this is the first thing that your book has given me that we've gone over. So it's been an hour, and I'm finally getting something from your book. That's a cynical comment there. Okay, this is a transient. Okay, do you see how that moved? Watch that. Okay, it's a very slow or very quick actually. It'll look slow here. Sort of instantaneous type of a thing. Dipole, look at that. You've got CH3, we've got an O here, so this is a negative coming this way, so you have plus end here. So what happens is you've got this is your plus end of the molecule here and the negative end here, so this lines up with this, and that is not transient. That's just always there, okay? So you've got that interaction between the positive end and the negative end. And then there's hydrogen bonding. Look at water. Okay? Very strong. Generally speaking, folks, that's how it goes. Okay? Generally speaking, that dispersion is lower, dipole-dipole is sort of intermediate, and hydrogen bonding is more energetic. Okay? Generally speaking. Because once again, think about something like water, H2O, pretty lightweight, and yet it boils at 100 degrees. It's got a lot of reasons to stay in the liquid phase. All right. This is for you to do. I want you to think about this right now. This is like a mini exam, okay? This is a good question. Well, it's not a very good question, but it's an okay question for an exam. So I want you to choose which of these is going to have the lowest boiling point. Now, before you do that, what does it mean to have the lowest boiling point? Don't forget, folks, the lowest boiling point means that you're the first one out of the party. You're the first one to leave the party, okay? Having the highest boiling point means you're the last one to leave the party. Okay, so once again, we're looking for the molecule that is going to leave the party first, which means it has the least amount of intermolecular forces. That's what that means. That's what this question is asking. So instead of saying which molecule has the least amount of molecular or intermolecular forces, I worded it in a little bit of a different way. Yes? Okay. So we got 4 choices up here. So I'm going to point to somebody. Or how about somebody raise their hand? Who wants to do which one? So you can do this by process elimination. Okay? Which one of these do you think is going to want to be a liquid for a while? Or wants to be in the phase that it's in? Who wants to raise their hand? Come on. You, yes. Xenon, she says. She says xenon. Why would you say xenon? Is there any hydrogen bonding? No. Is there any dipole interaction? Okay. Oh, okay. She's saying xenon is going to leave first. Are you saying what? What are you saying? Okay. That's not what I was asking. Okay. No, maybe that's what I was asking. I don't remember. Okay. Okay, so she says xenon. Okay, so she's thinking it's going to leave first because it has no dipole-dipole. It's got no hydrogen bonding. Okay, so this one is a possibility that it's going to leave first. Okay, then we've got who wants another choice? Another? Yes, you. Magnesium chloride. So you think it's going to leave first or not? Yeah. You do. Okay. Why?
It's smaller than xenon, so it has less dispersion forces, and it's not cold.
Okay. Okay. However, if you add all these electrons up, is it going to be smaller than this? Xenon's 54. If you add 17 and 17, and you're getting pretty close to being about the same size. The problem is this is kind of a bad question, because that is a salt. Okay, magnesium chloride is like Epsom salt, I think. And so it's just a salt. So it's really an unfair, that's why I said this would not be a good question, because of that one thing. So unless you would know that that was a salt, you know, so that's kind of unfair. So that is actually the highest, the last one to leave the party. That's like salt. Pour it on the table, salt just hangs around. But that's okay. Next. Okay, well, which one has hydrogen bonding? This guy right there has an OH. Now these hydrogens, folks, cannot be involved in hydrogen bonding. You understand that? Those three hydrogens right there cannot be involved in hydrogen bonding. Why? Are they attached to the OH? Or to the O? No. They're all bonded to the carbon. There's a hydrogen here, here, and here. Okay? This is bonded to that carbon. These are over here. It's kind of written kind of crappy, sorry. But, so the point is this has hydrogen bonding. So you can cross that off. That is not going to be the first one to leave the party, right? Because it's got a little bit of dispersion, but it's also got hydrogen bonding. So you can tell right away that guy's hanging around for a while. Now, it might not be the last one to leave the party, but it's certainly going to be there for a while. How about this one? Okay. So that one, does it have any hydrogen bonding? No. Lots of hydrogens, no hydrogen bonding. Okay. What's it got going for it? It's big. Yeah, it's big. And if you add up, you've got 5 carbons. That already gives you 60 electrons. Xenon has 54. And then you got all these hydrogens here. Okay. So we've already said this is absolutely not going to leave early. This one, because it's a salt, is not going to leave. So now we're down to these two. This has more electrons and is more dangly and wobbly than this is. And so this lady right here is correct. It is xenon. Xenon will leave first. Okay? And I believe I'll show you the boiling points right now. Okay, this is what we just did. Look at that. So this is dispersion, and this is dispersion. And look at the difference in boiling point, 166, and this is above room temperature. There's pentane in your gasoline. Okay, if it wanted to boil off real quickly, then what good would it be doing in your gasoline? Okay, so once again, dangly and wobbly is good. Even if it would have had the same exact number of electrons as this would be higher boiling because the dispersion is bigger. Okay? Do we understand? They all add up. Okay? This one had dispersion and it had hydrogen bonding. And this was just they shouldn't have put that in there. That was a trick question. And I wouldn't ask that because I didn't know it. Okay? I won't ask anything I don't know. I will ask stuff I don't understand. Oh, next one. No tricks on this one. Okay, I'm going to start calling on people. So what do we got here? What do we have that's common to all of them? They all have hydrogen bonding. OH, 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 and OH. Okay? So they all got hydrogen bonding. Yes? Oh, you're stretching. Okay. Yes? Last one. He says the highest boiling. Okay, so he's right. The question once again, when you say highest boiling point, that means you hang around the longest, which means most intermolecular forces. So we have hydrogen bonding in all of them, okay? But in 2 of them, how many hydrogen bonds can this one form? 1, 2, right? It's got 2. This has 1 hydrogen bond. This has 1 hydrogen bond. So if you looked at these 2 and you said which one has a higher boiling point, you would say this one, because it's got more dispersion. They have the same hydrogen bonding, but this has an extra carbon and 3 hydrogens, or 2 hydrogens, and so it has more dispersion. So this is going to have a higher boiling point than this. Water has 2. It's smaller dispersion-wise, but it's got 2 hydrogen bonds. Okay? This one here has 2 hydrogen bonds and is bigger than water. So it's going to form 2 hydrogen bonds, and this is 2 hydrogen bonds. And therefore, as you go this direction, it's okay, 1 hydrogen bond, small, 1 hydrogen bond, big, 2 hydrogen bonds, and then 2 hydrogen bonds and big. So this one is in fact the one that's going to have the highest boiling point. Do we understand that? Once again, you got to add things up. Okay, let's see what the actual boiling points are here. Look at that. Now, I might, folks, ask you if water has 373 degrees as the boiling point, estimate the boiling point of this. Okay? Now, would I expect you to get 471? If you wrote down 471, I would think you cheated. Okay? All you need to say is greater than 373. Because we don't know how much dispersion. It's just got that, I don't know. You see where I'm going with this? I want you to understand trends. I want you to understand that the boiling point of this is going to be higher than this. But I do not know how to calculate myself, nor do I expect you, that the boiling point of this is going to be 100 degrees warmer. Okay? It could have been 10 degrees. It could have been 100 degrees. I wouldn't say, I knew it wasn't going to be 1,000 degrees. But I wouldn't know that it was going to be more than 30, 40 degrees. But I want you to understand the trend. Okay? I want you to look at something and be able to say, this has this, and therefore it has a lot of reason to stay at the party. And the party is in whatever phase you're in. Okay? And once again, dispersion is this. Dispersion is floppy stuff, long spaghetti stuff. You ever made spaghetti? How many of you ever made spaghetti? How many of you let it sit a little too long before you took it out of the pot? And what happens? You reach in with those little things that have like those little wooden spikes on them or whatever, you know, that my wife has, and you pull it up like this, you get this big glob. That's how my spaghetti looks. Okay? You know, I look at my wife when that happens, I say, dispersion, get rid of this. I don't eat dispersion, no. But the point is that that's what it is. So you wouldn't have the same problem as bad if instead of long spaghetti things, you had made, what are those little tiny pastas? Elbows. Something called elbow? Yeah. Right? Like you make a macaroni and cheese. I can still stick them together. But they don't stick together as much because they're not as long. Okay? It's like having an extension cord that is unwound. Okay? If I had 10 extension cords in a big box, even if I had them coiled nicely, okay, if I reach in and grab the bottom one, I'm not going to get it out without grabbing some other stuff. If they're all coiled and actually tied together, like that, I can reach in and pull it out. So same molecular weight, but different physical shape makes a huge difference in terms of its dispersion. Okay? So once again, that's what dispersion is all about. And if you're talking about big molecules, then dispersion wins. Once again, the melting point, we saw this before, huge difference just going from hydrogens to here. And that is totally because of, not because in this case it's a polar, I mean not polar, but it's a symmetrical molecule. Okay, so there's nothing but dispersion going on here. And yet we look at this. This has a boiling point of bigger than water. Okay? Okay, so if we look at something that has four valence electrons, you add hydrogens to them, tin, germanium, silicon, and hydrogen. This is sort of the trend in terms of boiling point and the period, what you would get in terms of boiling point. You can sort of see this is somewhat linear, okay? But look at this one, HI, HBr, HCl, and then HF, way up here. We've got come down here like this, and then boom up to NH3, and then we come down like this and up here to H2O. Okay, and that is because the water, HF, and NH or N can all form hydrogen bonding. This is all because of hydrogen bonding. Okay, now the guy up here had asked earlier, why not chlorine? Chlorine, a little bit. Okay, if you look at this, you see how chlorine's starting to kind of creep up a little bit, but it's a little too big. Okay, it's a little bit too big. It's down one below fluorine, a little bit bigger, a little bit more diffuse, and so you tend not to have that as strong of a negative positive thing going to it. So yes, you could argue that chlorine has a small amount of it, but it's too small for you to worry about except for you, okay? So once again, this is all hydrogen bonding. If it had not been for hydrogen bonding, we would expect water to boil at about minus 100. Instead, it boils at plus 100. And we're darn lucky that we have hydrogen bonding, okay? Surface tension. Look at this. I like to watch those nature shows. I like the swamp people too. And you know, there's like this little lizard or something that can like run on the water. You know, it's got big web feet or something like this. But because of surface tension, it can do that. And surface tension is because it's kind of like you got all your friends down here holding on to you. This is like trying to get out the door. The door is here. And you're trying to get out and they're pulling on you. Yes?
Oh, I was just going to ask about the temperature. Why do we have to add 273 to get Kelvin? Or why do we work on that Kelvin scale?
Why do we work on the Kelvin scale?
Yeah.
Well, you just had to have to do it, because I said so.
Why do you have to add 273 to, or like?
Well, because a lot of the equations that we have come up with are based on an absolute zero.
Okay, and nothing can go below.
Nothing go below absolute zero. Yes. So it's not my rule, but I'm stuck with the equations. And so like we're going to do the Clausius-Clapeyron equation, and it's like 1 over T minus 1 over T2 minus 1 over T1. And if you put Celsius in, you're absolutely screwed. So you can never go wrong using Kelvin. Never. Just that you don't have a thermometer at home that says 373 is boiling. Okay, that's the problem. Okay, so this is once again, these are your friends, and this is the door up here. And these are your friends who really don't want you to leave. And so there's a tendency to have molecules kind of pulled back this direction toward the general populace. And that's what ends up actually allowing a mosquito to sit on top of the water, because the water is being pulled down like this. And this is this surface tension is all because of intermolecular forces, just like this. Look at this one. These guys have more attraction. These guys don't have it up on top. And so there's this net pull down. So it's almost like you got a little bit of a web up on top. Okay, there's just a little bit of a web up there. And that's why we end up forming, these nice little balls of water and stuff. When you have a nice cold drink, you'll notice that the whole outside doesn't get wet. It starts off like little bubbles. Okay, and so on. Okay, that's it for today, folks.